Assalamu alaikum everyone. Welcome to the class of interference of waves. Today we'll discuss something about um, the interference of waves, generally like for all the waves and then for light waves. So let's quickly go through the syllabus points. We are going to study interference and two-source interference. We have to study the terms of meaning of the terms interference and coherence. And then we will do study some experiments to demonstrate two-source interference using waterways, light, and microwaves. And then we'll study something about Young's double slit experiment, in which what are the conditions required for two-source interference, and then a specific equation developed by Thomson-Young, lambda equal ax by d, in his famous double slit experiment, in which he proved wave nature of light to solve certain problems. So for interference, you already know that interference is the interaction of two coherent waves traveling along same direction in the medium. Okay, then the next thing is conditions required for interference. So the two conditions required for interference, the one is waves must be coherent. Waves must be coherent. And number two, traveling along same direction. Traveling along same direction. And number three, must interact at a point. Okay, so these are the three conditions for interference to happen. Okay, then let's work on the types of interference. So as a result, when two coherent waves are interacting with each other, then two types of interference can happen. The first one is constructive interference. Okay, and the second one is destructive interference. Okay, about constructive interference, we say that crest of one wave falling on the crest of other and trough of one wave falling on trough of other. So I can just make it like this. Let's say this is the mean position and this is the first wave, wave P. And let's say a second wave is also coming over there and it's falling like this. They are interacting like this. So crest of one wave falling on the other and trough of the one wave falling on the other. And of course, amplitude of Q is bigger than amplitude of A. So what would be the resultant pattern? So here we go. You have to add both the amplitude, as the principle of superposition says that the resultant amplitude of two interacting waves is sum of the amplitude of two interacting waves. This is from principle of superposition. Okay, now what you will do is you have to add their amplitudes together and you have to work out for a wave. So let's say if if P is having amplitude of 1 and Q is having 2, then the resultant amplitude will be 3 units. So how you will be drawing it? You will be drawing it like this. So this is your resultant wave. And these two waves, P and Q, undergoes through constructive interference. And when constructive interference happens, then amplitude increases, right? And intensity of wave also increases. Okay, for destructive interference, the crest of one wave falling on the trough of other or trough of one wave falling on crest of other. So if I can draw the situation for you, let's say this is again wave P, and let's say this one is wave Q. So let's say they are having their amplitudes are exactly equal. Amplitude of X is equal to amplitude of, like amplitude of P is equal to amplitude of Q. So what will happen is that when you apply principle of superposition, they will be cancelled out each other and no wave will be formed. So this is your resultant pattern. Like all the the two waves are canceling out each other if their amplitudes are matching. But if their amplitudes are not matching, then any one wave will be formed, which is having a greater amplitude. So what will happen in this destructive interference, the amplitude will decrease and intensity will decrease as well. Okay, now let's work out on conditions of interference to be constructive or destructive. Constructive or destructive. So for constructive interference, we have to look for the conditions. So the first condition is that path difference between two interacting waves should be equal to n lambda, where n is the whole number. It means that the two waves which are meeting up together, they must be having a path difference of like 0, 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda, and so on. Or if the path difference is one of them, then only constructive interference will happen. Okay, what is path difference? Let me quickly tell you about path difference. Path difference is actually difference in paths moved by two interacting waves between their source and interacting point. So this is path difference. So path difference is, let's say, d2 minus d1. d2 is the distance moved by second wave, d1 is the distance moved by first wave. Let me elaborate it over there. Let's say this is S1 source, this is S2 source. Both of them are producing wave of the same wavelength lambda. And let's say this is the point P over where the waves have to meet up each other. So the path difference for this wave is S1P and for the other wave is S2P. So you will say that path difference is S2P minus S1P. So you will simply subtract these two distances to look for the path difference. And then for constructive interference, what you'll be doing is, for constructive interference, you will see that you will divide this path difference with lambda, right? And if your answer, like this answer, if your answer is a whole number, like if answer is a whole number, then interference will be constructive. Interference will be constructive. This is the condition for path difference. In the similar way, there is a condition for phase difference as well. Phase difference. So for phase difference, it's exactly the same condition. We say that the phase difference should be n into 2 pi or n into 360. So the waves, the interacting waves must be having a phase difference which is multiple of 360 degree or 2 pi, only then they can interfere constructively. Okay, number 2 is destructive interference. Okay, for destructive interference, we know that the path difference should be 2n plus 1 into lambda by 2. Or the phase difference should be 2n plus 1 into pi, right? Where in these two equations, n will be the whole number. Like for path difference, it should be like lambda by 2, 3 lambda by 2, 5 lambda by 2, and 7 lambda by 2, and so on. Or you can say odd multiple of lambda by 2. And for phase difference one, like for phase difference, it should be pi 3 pi, 5 pi, 7 pi, and so on. So it's again odd multiple of pi. So if this happens, any one of this happen, then the interference would be destructive interference. Okay, so these were the conditions for interference of light. Now what we have to do is we have to look for interference, and especially two-source interference experiments. Two-source interference experiments. These are the very simple experiment in the syllabus. They just ask you to describe the interference. So what type of question can come? Describe experiment. You have to describe that. And then a question can also come that discuss the outcome of interference in a particular situation. Okay, so the experiments which we will study are very like short experiment. The first one we will study with water ripples, how water ripples like two source interference in water using water waves or water ripples. Then we will study it using microwaves, the electromagnetic waves, of course. And then we will study about using sound waves. Sound is the like the longitudinal wave. And finally, we'll study light interference. That is our core topic over here. So Young's double slit experiment will be included in this. Young's double slit experiment will be included in this. Okay, let's move on to the first experiment, which is interference in water waves. In water ripples. So it's quite easy. What we have to do is we have to, let's say we are having this ripple tank. Let's say this is ripple tank. Okay, and then what we are doing, going to do is there is one vibrator and the motor is over there. And then what we are going to do is we are going to use, let's say, we're going to use, for example, one barrier over there. And then let's say over here, again, a barrier with two slits. So let's say this is S1 slit and S2 slit. So what will happen is if the waves are originating from here, let's say the water waves, these are water waves. So after passing through this, of course, diffraction will happen and these waves will be hitting the S1 and S2. So from S1 and S2, what will be happening is that the waves will be again diffracting. So S1 and S2 will be the two sources of coherent waves. So the coherent waves will be produced from here, and these waves are going to interact each other. So these waves are going to interact each other like this. So as the wave will move forward, they keep interacting with each other, right? So as a result, you know that what I have drawn, these are, let's say, crests. These are the wave fronts which are joined by joining all the crests. So what will happen is that the points where like two crests are being forming, like two crests are being forming. If you join this line, then constructive interference will happen over there. Constructive interference. And this line is known as antinodal line. Antinodal line, and all the maxima will be over there, like the amplitude will be maximum over there. And then there would be a line over which the minima would be there. And the minima line, let me draw the minima line with the blue one. Let's say this is the point, and then this is the point, this is the point, this is the point, and this is the point. So if you draw this, This is point where destructive interference is going on, and this is known as nodal line, and over here the minima would be observed. Why the maxima and minima are there? Maxima is there because crest is falling on crest, and minima is there because crest of one is falling on trough of other. So resultant displacement is decreasing. So it means you will see a series of bright and dark fringes. So what you have to do to look for the interference, you need two sources or slits in this case, which will act as a two coherent sources of light, like S1 and S2. Coherent mean they are producing the wave, having same wavelength, same frequency, same wavelength, and having the constant phase difference. So what is observed? What is observed over here? In this experiment, what is observed is you will observe series of bright and dark patterns in interacting waves. When the waves will interact, then you will observe series of bright and dark. Bright is, of course, when constructive interference is happening, and dark is when destructive interference is happening. So that's what is all about interference of water waves. Okay, number two is interference of sound waves, let's say. So how sound waves will interfere with each other? That's again quite simple. What you have to do is you have to take a loudspeaker. So this is loudspeaker one, and then take the other loudspeaker two. So let's say both these are connected to the same source of sound. And let's say over here is the distance. This is the line over which you are having a microphone. Like this is a mic, and you are connected this microphone to a CRO or to an intensity meter. This will be used to observe the interference. So what will happen is both of these, of course, loudspeakers will produce sound waves. So these sound waves will be traveling forward. And the other loudspeaker, of course, it will also be producing the same wave because both are connected to the same source. So what will happen is that the point where the crest of both the waves are meeting up, like this point, like this point. So at this point, the louder sound will be heard. So louder sound or high intensity. So if high intensity is there, it will account for constructive interference, like crest of one wave falling on the crest of other. And the other thing is, the next would be the antinodal. Like if blue one is the crest and the for black one, it is the trough. So if crest and trough are meeting each other, and if you place your microphone at this position now, then what will happen is that fainter sound, faint or no sound will be detected over here, or low intensity wave will be recorded on the CRO, and that will account for destructive interference because crest of one wave is falling on trough of other waves. That's how you can observe interference of sound waves by just using two loudspeaker connected to the same source, and then a mic with CRO or intensity meter, and the mic will be moving along this line, and you will observe series of like high intensity and low intensity patterns on the CRO. High intensity will account for constructive interference, and low intensity will account for destructive interference. Okay, number three. Number three is microwave interference. Okay, again, for microwave interference, what we will be going to do is we will be using two sources of microwaves, and this is the symbol for the microwave. Okay, and these two are connected to the same source, just like the loudspeaker. And over here is the point on which we have to move an antenna. So let's say this is an antenna which is moved because to detect the microwave, you need antenna. And then you connect it similarly to CRO or to intensity meter. It's the same thing. So this experiment is 100% similar to sound waves. You are just replacing loudspeaker with microwave transmitter over here. Rest of the things will exactly remain the same. So let's say if this microwave transmitter is emitting a microwave, it's traveling forward, and the other one is also emitting the same wavelength or the same frequency microwave, and it's also moving forward, right? So what will happen is that when these two waves will interfere with each other, then of course constructive and destructive interference will be happening. Let's say constructive is over there. So at this line, when crest will meet with crest, you will observe high intensity. So high intensity reading will be observed if crest of one fall on crest of other, and that is known as constructive interference. And again, low intensity pattern will be observed when crest of one wave falls on the curve of other wave. So that is microwave interference. Now we have to look on light interference. That is our main topic, light interference. So light was having a very interesting thing because light, right from the day one, the scientists were working on the nature or looking for the nature of the light. And the Newton view, Newton also said something about light, and he said that Newton's corpuscular, so Newton's corpuscular theory. Okay, so Newton said that light consists of particles. Light consists of tiny particles. Okay, as Newton was a great scientist of his era, so no one was like no one dared to stand against him. Although many scientists proved experimentally that light is having a wave nature, but as his reputation was too strong, that's why no one can deny the Newton's theory, corpuscular theory, even after 200 years of his prediction. Okay, then several other scientists came and they said that light is not having a wave, not having a particle nature, but having a wave nature. But of course, again, as I said, that his reputation was too strong, so no one can deny that. So Thomson Young was the one who did a famous experiment to finally prove that light is having wave nature. So Thomson Young's theory. His theory was that light is having wave nature. And he performed this with his famous double slit interference experiment. That is the same experiment we have to study over here. So let's study that double slit experiment. That is the last topic for today. Okay, so double slit experiment. What was the objective for this experiment? Objective was to show interference of light, between two coherent lights and to prove wave nature of light. That was the thing. Okay, now let's look upon the experimental arrangement. What things he used to prove this thing. So the first one is he took a light source and he took monochromatic light source. Monochromatic is the one which is having only one wavelength. Okay, secondly, two slits of width comparable to wavelength of light. So you use two slits which are having width comparable to wavelength of light, and then a screen to project interference pattern. So that was the simple arrangement. Okay, let's move on and see how his setup was there. So let me draw his setup. First of all, he used a light source. So let's say this is the light source. You can say it is a lamp. Okay, it is producing light. Okay, then he used to place a single slit in front of it, and then at some distance he placed double slit. And then of course the screen was there to just to make all the fringes on it. So let's say this is the screen. Okay, this is the screen on which all the interference patterns will be found. And just randomly making it in the blue color just to discriminate it. Okay. So over here is, let's say, the distance. Okay, so this is double slit. These are double slits, and this is like S1 slit and S2 slit, and then D is the slit screen distance. And then let's say if the light is being produced from here, so it's having wavelength lambda. Okay, and then what will happen is, another thing is small a. Small a is the slit separation. And then the fringe pattern will be formed over there. And let me quickly tell you about the fringe pattern. The fringes will consist of equal width of bright and dark fringes. So the central one is bright and adjacent to it are dark. So in the fringe pattern, every one fringe is bright and the next adjacent is dark. Okay, so this is dark, 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 and this is bright, bright, bright. So this is fringe pattern. So fringe pattern will be like series of bright and dark fringes will be observed. So what is lambda? Lambda is wavelength of light used. Wavelength of light used. What is A? A is slit separation, and it is measured in typically in millimeters. And what is D? D is slit screen distance, and this is typically measured in meters. And then one more thing is there, that is X. X. So X can be distance between center of two adjacent fringes. It's just like the wavelength, like the distance between two adjacent crest and two adjacent trough. So in the similar way, X is the distance between two adjacent bright fringes or two adjacent bright dark fringes. So X, you can say slit width, or oh no, sorry, not slit width. It's the fringe width actually. Fringe width or fringe separation. Again, this is measured in meters. So these are the things. And from all these things, he developed an equation for which the derivation is not included in our syllabus. And that is X equal lambda d by A. So this is the equation, X equal lambda d by A, where X is the fringe width, lambda is the wavelength, D is the slit screen distance, and A is the slit separation. Okay, so okay, now conditions for light interference. Okay, what was conditions for light interference? Number one, coherent lights should be there, and monochromatic light should be there. Monochromatic and coherent, and this will give you a pattern of bright and dark fringes on the screen. And of course, must interact. The light must be interacting with each other. Okay, how it works? The working is quite simple. Um, I have to take you back to the previous slide. When the lamp is switched on, then after passing through the first slit, diffraction happens and the waves are diffracting and traveling forward. And let's say uh, the two waves, similar waves, are falling on S1 and S2. And from S1 and S2 again, the same thing is happening, that the waves are spreading and moving forward. And from S2, the same wave is being generated and it is moving forward as well. So the waves are moving forward like this. And when the waves are moving forward, they are interacting with each other. So at some points, bright fringes will be formed, and at some point, dark fringes will be formed because the two waves which are moving forward, let's say moving this way, interacting this way, and this way, and this way, it will be constructive interference. So crest will be forming, will be falling on the crest of the other. And for dark, the crest of wave, one wave will be falling on top of other. So dark fringes will be observed over there. So that's how it works. Okay, so in first thing is production of light. So that is from one source, and then two slits are used. Two slits are used, and why two slits are used? To produce two coherent light rays, two coherent lights, like from S1 and S2. Okay, and then they interact, and interaction between coherent waves results in constructive and destructive interference, making fringe patterns on screen. Fringe patterns on screen. Okay, then let's talk about observations. Observation number one is that series of bright and dark fringes are formed having equal widths. So equal widths of bright and dark fringes are observed over there, number one. Okay, then let's talk about features of fringe pattern. Okay, beta, if we observe the fringe pattern, we'll observe that the central fringe is which one? Central fringe is, let me highlight that. Central fringe is, let's say, this one. This one is the central fringe. So the central fringe is brightest. Like its intensity is maximum. Okay, and for this, path difference was 0 and phase difference was also 0. And why is that? If I quickly draw it for you, let's say this is the first slit and this is the second slit. And let's say over here is the screen. And this is where the bright fringe is formed. So this is central bright fringe. Central bright fringe. So what is happening is that from S1 wave is moving and from S2 the wave is moving. So both waves are like if this is O, so S1O and S2O. So it means that both are covering the same distance. That's why path difference is 0 and phase difference is also 0. That's why the central fringe is bright and it is having maximum intensity because it is at the closest position to slits. So it is having closest position to splits. That's why the intensity is maximum, because we will be following this thing in the intensity, inversely proportional to d squared. Okay, moving forward, let's look for the first bright fringe. other than the central, like bright fringe next to center. And let me take you back, and I am talking about this one. So this is like N1, or this one, this is N1. So N1 means the first bright fringe after the central. So for that, the part difference is 1 lambda, or the phase difference is 2 pi radian. And if I can draw that situation for you, let's say these are the slits, and this is the screen, and I am talking about, like, this was the central bright fringe 0, and then of course our dark was there, and then this bright is N1. I'm talking about this. Or similarly, this is dark and this is bright, so this is N1. So I'm talking about that N1, this N1 and this N1. Okay, so now let's see that if this is S1 and this is S2, so from S1 a light is going over there, and from S2 a light is going over there, and they are interacting. So we can give that name as 1. So S1 1 and S2 1. So of course the part difference between them should be 1 lambda. So from S2 one more wave would be reaching over there. So that's why the phase difference is 1 lambda. So it will be bright, but its intensity will be less. Intensity decreases because this thing has moved away from the source, moved away from source. And what are the sources? The slits, S1 and S2. That's why its intensity will decrease. Okay, now keeping in mind, let me tell you about the dark fringes. Dark fringes, and dark fringes mean that, let's say this is again the two slits, and this is the screen. So two slits and the screen. So what will happen is the central will be the bright one, and then next will be the dark one. So I'm going to tell you about this. This is the first, like the dark. So how the dark fringe will be formed? This is S1 and this is S2. So from this light is coming, and from this light is coming as well. So the part difference between these two rays, like 1 and 2, this should be part difference between 2 and 1. This should be equal to lambda by 2. Or the phase difference between them should be equal to pi radian. That's why a destructive interference will happen. So summing it up, overall, the fringe pattern would be, let's say, so 1, 2, 3, 4, 5, 6. Okay, so this one is bright, bright, and the other one is dark. So this is dark, dark, dark. And let's say this is the central. So we say that this is central maxima, and it's having maximum intensity. And this is for the dark N1, and this is for the bright N1. This is for the dark N2. This is for the dark N1, for bright N1, and for dark N2. So actually on both sides of the mean line, the mirror image is there. The fringe, the number of fringes which are making above the central line would be same as the below the mean line. So path difference condition for this would be 0. For this, path difference would be lambda by 2. For this, path difference would be lambda. For this, the path difference between interacting waves should be 3 lambda by 2. Similarly, over here, the same thing, path difference should be lambda by 2. Path difference between interacting waves should be lambda, and path difference should be 3 lambda by 2. And if I make the intensity spectrum for this, it would be 0 and a bit more, and 0 and a bit higher side, 0, a bit less, and 0. So this is intensity. intensity spectrum. So the high peak shows that this is highest peak. It shows that the central fringe is brightest. And as you move away, so it shows that as distance increases, intensity decreases. And the same is over here. As you move away from the central, as distance increases from the center, the intensity decreases. Okay, next thing is the calculations. For calculations, you will be using only one equation, that is x equal lambda d by a. And as I already told you, let me tell you again, this x is fringe width, or this is also known as fringe separation. And its actual unit would be meters. And this lambda is the wavelength of the light used in meters. This D is slit screen distance, slit screen distance, and it would be in meters as well. And this A would be slit separation, and slit separation will be in meters or millimeters as well. So all the units are of length. Okay, now the trick can be there in X. This X can be tricky. Otherwise, everything will be straightforward given. Why X would be tricky? Because sometime, let me take you back, they can ask you that, look, the distance between center of N2 and center of this N1 is, let's say, 10 millimeters. I'm overwriting it just to tell you quickly something. So out of this, you have to figure out X. You will say that this 10 millimeter between the two dark patterns on the over here is not actually X, but it is like from this dark to this dark is 1, and then this dark is 2. So you will be saying that actually it's like 2x equal to 10 millimeter, and then x would be 10 over 2. So you'll be writing x as 5 millimeters. So this is the trick that can be there for x. Okay, the next thing is, what are the factors, the last thing for today, factors affecting fringe pattern. Okay, so for fringe pattern, we'll be looking on two things. One, how x is changed, like fringe width. And number two, how intensity of bright fringes can change. Intensity of fringes can change. So these are the two things we are looking at, and that is the last thing for today. Okay, so talking about the factors, the first three factors are coming from the formula, like x is lambda d by a. So if you look carefully, x proportional to lambda, x proportional to d, and x inversely proportional to a. So it means fringe width can be affected by these three things. So let's look on the first one, which is wavelength. Wavelength or frequency of incident light, how that can affect the fringe width. So from the relation, it is clear that x is proportional to lambda. And one more thing, we also know that frequency and lambda are inversely proportional to each other, right? So so that's the thing. So if you increase lambda, if lambda is increased, technically you are decreasing frequency. It's the same thing, like increasing lambda or decreasing frequency, both are same things. So when you do that, then x would increase as well. So you will say that now wider fringes are formed. So wider fringes are formed because x is the fringe width. So if lambda increases, x would also increase. Okay, for intensity, we know that intensity proportional to frequency square. From the previous chapter, we know this thing. So as you are, let's say if you are increasing lambda, so you are decreasing frequency. So when you are decreasing frequency, so actually intensity will decrease. So intensity of bright fringes will decrease. So the intensity will decrease. So the fringes intensity or the brightness will be decreasing. Okay, Number two. Number two is slit screen distance. Slit screen distance. So as the relation, according to the relation x proportional to d, and for intensity, you know I inversely proportional to d square. So what it will, how it will impact is if you increase the distance, then x will be increased, means wider fringes will be there, wider fringes. And as x increases, as d increases, you know, intensity decreases. So intensity of the fringes will decreases, because when you move the screen away from the slits, of course, less light will be reaching over there. So the fringe intensity will be decreasing. Okay. The third factor is um, slit separation. Slit separation. So from the equation, it is clear that x inversely proportional to a. So if you are increasing the slit separation, like moving apart, the two slits are moving apart, then as x is increasing, x should decrease. So x should decrease. So we will say that narrower fringes, like the fringe width decreases, right? And it will have no impact on intensity because there is no relation of A with intensity. So no intensity change for fringes. Okay. Lastly, number four, if slit width is changed, like you're not changing A, you are keeping A, D, lambda constant, but you are making the slits wider, right? Slit ke beech mein gap, the gap between the slit is increased. So what is that gap? Let me take you back. This gap between S1 and S2, like this width, the width of S1 and S2, that is being increased. So when you will increase that, what will happen? Like X will remain unchanged because X is not affected by that, but intensity will increase. Intensity will increase because more light will be falling on will be passing through the slit. So that was our topic for today. I hope that you got all the points. So what you have to do is you have to make notes uh, of it, and then for the problem solving, if anything is problematic for you, then you can WhatsApp me today, but try to cover up this topic for sure by today. Thank you so much. Take care, everyone. Allah Hafiz.